All right. Not only software, but also hardware nowadays suffers from vulnerabilities. And to improve the situation, we created CellIFT, the first mechanism for dynamic information flow tracking for hardware that supports out-of-order CPUs. You may be familiar with these logos. They represent hardware vulnerabilities, difficult to fix, but you may know also extremely difficult to find in the first place. And there is one fundamental insight that makes our work possible and interesting. It is that these bugs and many others are expressible as information flows. Let me give you some intuition. So on the left side, there is the CPU core. On the right side, memory. In the middle, some microarchitecture. So let's assume the CPU up does a load from some privileged data that I first tainted. So up, let's do the load, path. So the data, along with the taint, traverses the macroarchitecture to finally influence some state in the core. And now if an attacker exfiltrates some data, it will be quite easy to find in principle. You just look, is there some orange taint where I did not expect it? So this is something that we want to achieve. Actually, there is already one mechanism that supports dynamic information flow tracking for hardware. It operates at gate level. It's called GLIFT. What does it mean, operating at gate level? It means that you take a design, a CPU, for example, poof, you break it down into very, very small elements. So AND gates, OR gates, registers, no, actually not even registers, flip-flops, sorry, and latches. So very small elements. And then Glyph takes every of these very small elements, very many elements, but very small, and adds some information flow tracking logic around it to track information flows through each of these very small elements. This is how it works. This very low level of abstraction has drawbacks, critical drawbacks. First, it creates a huge netlist that is extremely difficult to manage for tools. Oops, sorry. And also simulators have a very hard time with it because typically, to be fast, a simulator will see higher level of abstractions. For example, it will see adders. And when it sees an adders or a comparison, for example, the simulator just sees, oh, it's an addition. So let's just run it on the CPU of the machine instead of, doing AND or etc. just to simulate an addition. Doesn't make sense. But here you need to do it. You need to simulate every single individual gate, which is extremely expensive. So very intuitively, we propose to instrument a higher level of abstraction, the abstraction of macrocells, also called cells in short, which correspond to simple mathematical operations such as additions, comparisons, multiplexers, subtractions, etc. And then, same thing, but for bigger blocks. So for these big blocks, I add some logic around them to track information flows around them dynamically. The question is, what are these clouds now? This is a new question. Let's try, again, some intuition. So I will look at a combinational cell which does not have state inside. For example, a register would be excluded, but it could be another. So here, I give you two tainted inputs in orange, and I want to know, oh, is some output bit tainted or not? You can see for your intuition, you can imagine you have an attacker. It controls the two orange arrows. The question is, can the attacker change values on the output if it only controls the two orange arrows? Let's do the intuitive way. I try everything that an attacker can do. 0, 0, 1, 1. Up, we see that we could toggle the bottom output bit, so it's tainted. Okay, I continue. Poof, poof, voilà. We could not affect the top bit, so exactly only the bottom bit is tainted. So this is something that we want to do. In practice, in hardware, we like to do stuff in parallel. And actually, in this case, we even must. And we also need to adapt for the most complicated part, which is that everything is actually tainted as the input, because taints are determined dynamically, whereas the instrumentation is static. So we copy the same cell 16 times in this case, 16 times because we have 4 inputs. So combinations of 4 inputs, you have 16, 2 power 4. And you provide different inputs for each of these replica that change only the values on the orange arrows. For example, here, you put only zeros to the orange arrows. Here, 1 at the bottom and the rest zeros, etc. The idea is really to try all the combinations on the orange arrows. In the end, we also compare the outputs. The idea is to know which output is actually tainted and which was not changed in any of these replica. You may see the problem. Imagine you have just one adder, 64-bit adder. This is quite common. You need 2 power 128 replica of it. You imagine that this is completely unrealistic. Now the question is, how do we get rid of this exponential dependency? So we have a certain number of inputs, and if there are many, then we have too many replica. How do we make it maybe a constant number? I will show you how to do only 1 or 2 copies, 1 or 2 combinations if you prefer. We do it by identifying 3 properties of these cells: monotonicity, transportability, and translatability. Here are some cells, for example, that correspond to these 3 properties. I will limit myself to this cell, this inequality cell, but I promise you will get the big picture. Okay, so let's look at what would be monotonicity here. So here we have 2 inputs, up. The left input, if you increase it, you can only decrease the output. On the other side, if you increase the right output, there is a chance that you can actually increase. So if you increase the right input, you may increase the output. So these are some monotonicity properties, and this hints the fact that you can look at only 2 combinations or 2 replica. One that minimizes the output and one that maximizes the output. All the rest we don't care. Example? I tainted arbitrarily 2 bits on the right, 2 bits on the left. Up. First I minimize the output, so I maximize left, minimize right. And I do the opposite, I maximize. I see, oh, it's tainted if and only if it's toggled. Here it's toggled, answer, it's tainted. Okay, so up, 2 replica, promise held. Of course, this was for a simple case. We have 3 properties for a total of 22 combinational cell types, and also many variants of registers, for example. So our implementation is a pass in the USENIX open source synthesizer. For the people who are not familiar with that, this is the equivalent of a LLVM for hardware, more or less. So we just take a design as an input on this side. So, and this design is a netlist of cells, idiomatically. And we output another design, which is the same design, but plus information flow tracking logic around it, a bit like I explained at the beginning. Now let's speak about results. First, I will show scalability results for individual cells. For example, how an adder becomes scalable. Second, which is the most important in my opinion for a mechanism, how does this scalability now transfer to actual improvements in actual designs, such as CPUs and SoCs. And finally, I will discuss some applications. So this is not us. This is the state of the art. So on the y-axis, you have the simulation time. And on the x-axis, you have the size of the cell. Let's focus on the adder. So if you think about an adder, let's take a ripple carry adder. So you have this carry chain. And the more input bits you have, equivalently the bigger your adder is, the more elementary gates you have, or AND gates. And because gate-level instrumentation requires you to simulate each of these gates, then the runtime is linear, right? More gates, linear. But CellIFT works differently, because CellIFT adds a constant number of cells, and these cells are run in a constant number of constant time. So constant time constant, this is us, constant. So this is scalability results for individual cells. Now, does it translate to improvements in real designs? To answer this question, we took 5 popular RISC-V based designs of arguably increasing complexity, including a full SoC, and including an out-of-order CPU. We run quite standard RISC-V test benches on it in simulation, and the question is, how slower is the simulation of the instrumented design compared to the normal design that is not instrumented? Here's the results of this experiment. There is 2 takeaways. First, some more complex designs could not be instrumented and simulated by the state of the art. Even on a 1 terabyte machine, this doesn't work, because it's so low level, requires so huge netlists. For CellIFT, no problem. For some designs, we could instrument and simulate them with the gate level solution. This works. However, CellIFT makes it much faster. Okay, finally, some applications. First, CellIFT allows you very idiomatically to find macroarchitectural elements that leak or potentially may leak data. Second application, we took full-fledged SoC and rediscovered bugs with very simple policies. Third, we did Meltdown experiments, found negative results for Ariane in some scenarios, and in some scenarios we could confirm positive results and increase the state of the art in terms of exploitability on the Boom processor by showing that some scenarios are not exploitable. And finally, we did some Spectre experiments with positive and negative results on Boom, and we could quantitatively evaluate the speculation window of Spectre on Boom. And the nice thing is, in all these experiments, we did not need a single cache attack. So this is also very new and extremely convenient if you want to have very precise results. Also, if you don't want to do cache attacks because it's boring. OK, time to conclude. CellIFT is the first mechanism that can instrument and simulate out of order CPUs, or any CPU that we could try, at the time of the writing at least. It's much faster than the state of the art for some designs that could already be instrumented and simulated. We have new applications. So for example, detecting leakage through Meltdown, through Spectre. But we are convinced that there are new applications that we did not think about, or that we are working on right now. We don't know if they will succeed. But there is new applications. And to help you debug your own designs and find new applications and maybe present them here next year or the year after, or maybe 5 years, we make CellIFT open source. It's also artifact evaluated. I didn't show it here. I will do the best possible to support you. Feel free to try. Thank you for your attention. Please ask questions if you need.